Good morning. To the left you can see the PV diagram for a Carnot engine cycle. The idea behind any engine cycle involves a power stroke where the gas pushes out against its environment at high pressure, and then an intake stroke where the gas is compressed at low pressure. The work done by the gas during the power stroke is equal to the area under the power stroke curve on the PV diagram. Actually, let's just label those axes on the PV diagram, just to make sure it's clear. Now, again, the area under the curve on the power stroke equals the work done by the gas, and then the area under the curve on the intake stroke is equal to the work done on the gas. If more work is done by the gas than on the gas, then the cycle produces work. The cycle is converting heat into work. Now, one key concept behind the Carnot engine is that the only processes involved are isothermal. These blue lines are the called isotherms, and adiabatic. The red lines here, or curves, are called adiabatic. Now, there's really only one natural example that I can think of where an expanding gas does work at constant temperature, and that is where the balloon underwater climbs up, working against the gravitational force. This would be isothermal if the water is at constant temperature and remains at thermal equilibrium with the air in the balloon. On the other hand, adiabatic compressions and expansions are fairly commonplace. If you sealed the end of an air pump for instance, and compressed the gas in the container, that would be an adiabatic compression. Likewise, if you then let go of the handle and let it pop back up, that would be an adiabatic expansion. So let's imagine this more familiar part of the cycle to start with. We're going to put a tiny bit of air into a chamber and compress it from about 14 cubic meters to about 6 cubic meters. During this time, the gas will heat adiabatically from 54.88 Kelvin to 101.15 Kelvin. At this point, we will put the container in a 101.15 degree heat bath. Okay, now there's one caveat. If the heat bath is greater than 19 pascals at this point, the gas is really going to continue to shrink. But if the heat bath has a really low pressure, like 5 pascals, then the gas will grow isothermally to 20 cubic meters, i.e. doing work on its environment. Now we take the gas out of its heat bath, and as long as the pressure around it is low enough, it will continue to the gas will continue to expand. It expands adiabatically, which means that its temperature is dropping. And once its temperature reaches 54.88 Kelvin, we put it in another heat bath. But this one has a higher pressure than the gas. And will cause it to compress isothermally until it reaches 12 cubic meters and about 4 pascals, which is back where we started. So you see, there are two requirements at each stage. For adiabatic compression, you need ambient pressure higher than that of the gas, and you need insulation so that the gas can go up in temperature. For isothermal expansion, you need an ambient pressure lower than that of the gas, and you need an isothermal equilibrium with some kind of heat source, here at 101.15 degrees Kelvin. For adiabatic compression, again, you need an ambient pressure lower than that of the gas, and you need so that the gas can change temperature on its own. And then you need to put the gas in a higher pressure cold bath for isothermal compression. So again, you have high pressure insulated environment, then a low pressure heat bath, then a low pressure insulated environment, then a high pressure heat bath. Now this manipulator I made in Mathematica took me quite some work the other day. Quite frankly, it took a long time just to figure out where to start with it. My final version made the pressure and volume at point 1 at the end of the isothermal compression and point 3 at the end of the isothermal expansion as our free variables. From there, though it was not at all easy, I was able to figure out both relationships for P of t and V of t for the adiabatic curves. So, I was able to find P0, V0 based on P3, V3 and going from the cold temperature to the hot temperature. And I was able to find P2, V2 based on P1, V1 and going from the hotter temperature to the colder temperature. You can see the final result right here. P2 is based on P1 and the ratio of temperatures final to initial. V2 is based on V1 and the ratio of temperatures initial to final. Likewise with P0 and V0. These were derived by solving two equations to unknowns. One of the equations came from the ratio of the ideal gas law, and the other one came from the adiabatic pressure-volume relationship. Now, I just arbitrarily decided to set the number of moles equal 1 divided by 8.31 so that N times R would equal 1 joule per Kelvin. Then I solved for T1 and T2 using the ideal gas law twice, knowing P1 V1 and P2 V2. Actually, I solved for T1 and T3. T2 and V2 are the only unknowns in each of these two equations, so they can be solved for. Once I had the PV coordinates of the four vertices, it was a matter of finding the curves between them. The isothermal curves were accomplished by pressure times volume equals constant, and the adiabatic curves were established by pressure times volume to the power of gamma equals constant. Then it was a matter of basing the isothermal power stroke on point 0, the adiabatic power stroke on point 1, the isothermal intake stroke on point 2, and the adiabatic intake stroke on point 3. And furthermore, graphing each process over the appropriate domain, the isothermal power stroke from volume 0 to volume 1, the adiabatic power stroke from V1 to V2, the isothermal intake stroke from V2 to V3, and the adiabatic intake stroke from V3 back to V0 again. Then, by manipulating the PV starting points, we can see a range of different Carnot engine cycles.